Holschuh on the influence of solid Earth on ice sheet stability.
Thank you very much. And I wanted to take a second to thank the conveners for inviting me. Before I came, I was talking to my brother and I said, this group invited me to come give a talk in northern Italy, and his response was, why would they do that? And, after briefly considering whether or not, considering whether siblings are a net positive or negative in life, I reflected on that question, why would they do that? And actually, I think I bring a somewhat different perspective to this general question of what is the influence of the solid Earth on ice sheet stability as a radioglaciologist. And so my hope today is to share with you some of that perspective that's more focused on the interface between ice and its substrate. So since we realized that ice was transparent to radio waves, the general principle behind radar sounding has pretty much been the same. If this is our ice sheet system here, this is the ice surface, this is the ice bottom, and this is us with our radar. The way radar imaging works is you send out an electromagnetic pulse into the subsurface. When that electromagnetic wave encounters material contrasts, some of that energy is reflected back to the surface, where the radar is measuring the strength of the electromagnetic field. And so if we know something about the speed of light in ice, just by measuring the backscattering of that electromagnetic pulse, we can start to characterize the subsurface. And as I said, the principle behind radar imaging has been pretty much unchanged in the last 50 years. You measure the character of the returned wave, you say something about the subsurface. But what has changed in the last 50 years is there's been a tremendous amount of work in radar engineering by folks in this room. Dusty and Duncan and others have worked to improve the quality of the hardware, the precision of the measurement, and the types of things we can do with radar hardware. And there's been dramatic advancement in signal processing. And with those two sets of kind of technology advancement, we can be more sophisticated with the experiments we run using radar systems in Antarctica and Greenland. So just to note, if you take this instrument and you drag it across the surface with a skidoo, or you fly it across with a plane, you collect lots of these traces, and you can convert the numbers in these wiggles to colors in a pixel, and you get these beautiful images of the subsurface, the layering within the ice sheet, the glacier substrate. My goal today is to answer two kind of related but somewhat different questions. The first is, how can radar help us better predict the nature and timescale of unstable glacier retreat, which is one of the central questions that's being investigated here at this meeting. But one way of thinking about that question is, what can modern radar systems measure, and how do those measurements inform our understanding of glacier sliding, which is a critical component to the marine ice sheet instability. Before I got too far, I wanted to acknowledge that a lot of the work that I'm presenting today is work from my colleagues and collaborators from around the world, funded by a diversity of organizations, the National Science Foundation, NASA, through big collaborative projects. And also, I want to acknowledge my wonderful students, just because they're amazing, but also because they contributed to all of this work. So to think about this question about how radar can be useful, we have to start with some understanding of that marine ice sheet instability that's the topic of conversation this week. The underpinning of the marine ice sheet instability is this feedback cycle, where forced thinning at the margins of the ice sheet leads to ungrounding at the grounding line, acceleration of the ice sheet, and additional thinning so that this cycle can proceed. This additional thinning is predicated on a flux divergence at the grounding line, more ice flowing out to the ocean than is replacing it from upstream. And that flux divergence doesn't just depend on what's happening here, it depends on what's happening in the interior of the ice sheet. Because you can have acceleration that doesn't induce a flux divergence. If you're replacing new ice at the grounding line as quickly as it's evacuating to the ocean, you're not actually going to thin, and you're going to slow the marine ice sheet instability. And so this question of differential acceleration from the margins to the interior is really a question of glacier sliding and the physics of glacier sliding. How well does the bed prevent acceleration here from also accelerating ice here to replace the ice that's being lost to the ocean? When I realized I was speaking in this general session around the solid Earth, I went back to Pippa Whitehouse's review article about all of these solid Earth processes that have been, the folks of great talks in the hours preceding now, the idea of deposition and erosion, glacial isostatic adjustment, geothermal flux, those processes are coupled into the ice sheet because the substrate that is defined by these geologic processes is both a geometric and material boundary to the ice flow problem. And so understanding it as a geometric boundary and understanding it as a material boundary is essential to predicting the future of glacier sliding. As a geometric boundary, it matters because the geometry controls the local ice thickness gradients and the flotation criteria, which are essential to both the marine ice sheet and the hypothesized the marine ice sheet instability and the hypothesized marine ice cliff instability. The geometry of the substrate defines the grounding line geometry and the access for warm water to the grounded ice sheet. It also acts as an obstacle to flow. So understanding all of these things are important. It's also a material boundary, which means it defines the mode of and resistance to glacier sliding. Whether or not it's a hard bed filled with cavities with subglacial water or it's a soft bed matters for glacier sliding. It also controls the heat production and delivery to the ice bottom interface and therefore the thermal state, a control on glacier sliding. So the question I want to pose is, can radar data help us understand the geometric boundary at the base of the ice sheet? The answer to that question is fairly obvious. But can it help us understand the material properties of that boundary? And can it actually help us understand the process of glacier sliding? So glacier sliding is this wonderfully studied topic, richly complex field, because it's kind of a catch-all term. Glacier sliding is not one process, but it's many processes. It's all of the processes that govern the relationship between the stresses in the glacier substrate and the ice flow. And back in the 1950s, Weertman wrote this wonderful paper on the sliding of glaciers, where he had simplified the problem to this ice sheet that is not mechanically coupled to the horizontal surface underneath. There's a thin water layer that separates them. But it's really these geometric obstacles that govern the stresses that resist glacier sliding. And from the Weertman tombstones, he derived a glacier sliding law, a numerical framework for relating stress and speed. Since then, there's been kind of a proliferation of experimental and observational and theoretical studies to better understand glacier sliding that all produce their own empirical or theoretical relationship between stress and speed. And I want to highlight two of these experimental results just to show the kind of wide range of models that we get for this interaction. So Luke Zoot and Neil Iverson have a ring shear experiment where they compress ice, they can control the rate that ice is forced past its substrate, and they can measure the stresses. And what they found is on a hard bed, on bedrock material with some subglacial geometry, you derive a particular sliding law where as you increase the speed, the shear stress, the resistance to flow, increases until you reach a certain threshold where you're opening up cavities in the subglacial environment. And then the shear stress that the bed provides decreases with increasing speed. They ran that same experiment, except instead of using a hard bed and bedrock, they used till that has clasts in it. And what they found is this other relationship for glacier sliding, where you end up plateauing where there's no change in stress with speed. And what I want to highlight is that both the geometry, the obstacles to flow, the material characteristics, whether or not you're bedrock or you're soft sediment, those things change the physical law that governs the interaction between ice and its substrate. And so here are just 4 examples of sliding laws that are published in the literature, and we don't have a good observational basis for choosing one of these sliding laws in many places in Antarctica. But our choice of sliding law changes the rate of the instability associated with ungrounding at the margins. So there are a series of papers that were written by Byron Parizek and his students looking at both flow line models and plan view models of glacier retreat in the Amundsen Sea embayment. And they run these same models with the same marginal forcing, but with different glacier sliding laws. And so here's a flow line model of Thwaites. This is using a particular sliding law, linear viscous sliding law, that allows the bed to strengthen dramatically as the flow speed increases. And what they found is that with this linear viscous sliding law, the flux divergence at the margin was high. That is to say, the interior couldn't accelerate when there was a marginal forcing. And so that causes dramatic thinning just at the margins of the ice sheet, which reinforces this ungrounding, acceleration, thinning, ungrounding, acceleration, thinning feedback that defines the marine ice sheet instability. And so for Thwaites, with a linear viscous sliding law, even though you really don't see much of a response in the interior of the ice sheet, what you see is this rapid ungrounding. If you apply one of these Coulomb sliding laws where you can perturb, the interior ice feels the marginal stresses, it can accelerate much more readily in response to marginal forcing, you actually have reduced grounding line retreat because ice at the grounding line that is fluxing to the ocean is being replaced by ice from the interior. And so in both of these cases, you have thinning in the interior, but the grounding line has not progressed further back in space. And so understanding what sliding law best represents the materials that underlie the ice sheet is critical to predicting the timescale of a marine ice sheet instability. There's an interesting result that came out of the same group that was looking at what happens if you apply a spatially variable basal sliding law. This figure is a little bit hard to parse. The x-axis is time. So in this model experiment, time 0 is the start. The y-axis is the position of the grounding line. And so as lines move down, you're looking at grounding line retreat. And this is an idealized bed geometry where they applied either a uniform linear viscous sliding law, a uniform plastic sliding law, or a spatially heterogeneous sliding law, and figured and evaluated how the grounding line retreats. The original thinking when this started is that these two, this viscous or this plastic law, may be end members to the system. So if you apply a linear viscous law, you have this black curve. It retreats first, just like the previous results. You concentrate thinning at the grounding line. You step back by the marine ice sheet instability. The nearly plastic one hangs on longer to the topographic high because ice can be replaced to the grounding line. It eventually steps back as you drain the interior. But curiously, when they applied a spatially variable sliding law, one where there was linear viscous in some places and plastic in others, they got a result that fell outside of the two end member cases. And so now not only do we have to know what sliding law is best to prescribe for our ice sheet model, we also need to know how it varies in space, what the heterogeneity of that sliding law is in space. So all of that is to say that the constitutive relationship for basal sliding is both material and geometry dependent. So we need to know about the details of the material and the geometry. The sliding law governs the rate and magnitude of the marine ice sheet instability. And substrate materials likely vary in space and are poorly observationally constrained, which raises this big opportunity for an observational basis to improve our modeling of this particular process. So for the rest of this talk, I'm really trying to answer this question: can radar measure heterogeneity in basal properties or help us better understand the physics of glacier sliding? And to do that, I just want to introduce two kind of technologies, one that we've tested quite a bit in the field, one that's more in development that might help us address that question. So the first technology I want to talk about is something called multi-element array processing, or swath radar. And I like to just give a moment of history about a multi-element radar. Multi-element radars were kind of popularized in the early 2000s when it was proving difficult to image through the thick, warm ice of Greenland and still see the bed. And the benefit of a multi-element radar comes from the fact that they're more directive. So if you just have a single radar antenna screaming into space, I'm going to clap because I always do this with my students, that sound is radiating uniformly. And it turns out that's really deleterious for imaging what's below you for a lot of reasons. You're wasting energy sending it out at wide angles, and so there's energy loss, and you get clutter off of scattering from places that you don't care about. So it turns out if it's not just one element clapping, but you have 10 elements, the constructive interference of the waves transmitted by those antennae makes the signal stronger below you and weaker to the sides. And so most airborne radar systems that have been flown in the last 20 years involve more than one antenna element for the purpose of being more directive, sending more of their energy down. But it turns out having a multi-element array allows you to do more sophisticated signal processing of the returning radar wave. So if the radar signal is coming from below the plane, and it's coming up in this case as a plane wave, you might expect that it will arrive in time and in phase for every element in your array. Exact same time here and here. But if the signal is coming from the side, you'd expect that the signal would sweep across the array. It would arrive here first and here last. And so you can start to use the information from the multiple elements of the radar system to determine the direction of arrival of your scattering in the subsurface. So if this is our conventional radar image, for every single one of these time series, you can ask yourself, how much of this energy that we're seeing is coming from our left? How much of that energy is coming from our right? And you can measure the subsurface in multiple dimensions. So as the plane flies over the system, we can trace out scattering from the left, from below, from the right, and you can map out not just a line, but a swath of the topography underneath the plane. So when you apply this technology at scale, you can start to image both a long track and a cross track roughness and get details of the topography that we haven't had before. So here are two grids of subglacial topography that were collected at Thwaites Glacier, about 100 to 150 kilometers, 250 kilometers upstream of the grounding line. And by looking at these, you can start to see some qualitative difference in what's going on in the subsurface. You see these lineated features, you see this kind of isotropically rough topography, things that probably matter quite a bit for the interaction between ice and rock and eventually ice and the ocean. For example, this is bed map 2. The difference between bed map 2 and this topography here are nearly 1,000 meters of relief in some of these local features that we see in the topography. Water routes through this area. You might expect that ocean could engage with the ice if this were the grounding line at this location, indicating that this high-resolution geometry is actually quite essential for understanding how this system interacts with the ocean and how the glacier interacts with the ocean and the rock underneath. So one question is, can we use these high-resolution topographies to better understand the physics of glacier sliding? So one thing that we've done is we've thought about this problem of drag imparted by the substrate. And you can decompose the drag that the substrate applies to the ice into two kind of conceptually different things. One is form drag. Form drag are the geometric obstacles to flow. In a perfect ice sheet model, we have an infinitely precise geometry, and form drag is fully captured by the stresses inside the ice itself. The other component of drag is something we often call skin drag. This is drag applied at the interface, not by stresses within the ice. And the dream is to be able to deconvolve these two things because they actually are represented by two very different physical processes. What we found is if we take this grid and we smooth it, we look at it in its full detail down to like 5 kilometer smooth product, and we calculate the skin drag applied by the bed. We use an ice sheet model to calculate the stresses, infer the drag. What we see is as we smooth the topography, that the inferred skin drag goes up, which is what we would expect. We're taking the form drag component and we're mapping it into the bed because we don't have the details of the geometry that are essential for capturing form drag. We're essentially taking stresses that were in the ice and now we're applying them just to this interface. One interesting thing about this result is that even with our highest resolution topography, our roughest substrate, the thing that's doing the best to capture the geometry, it looks like we're nowhere near yet fully resolving the effects of form drag. We don't see any tail off of this change in the friction coefficient, which argues for the fact that glacier sliding is this combination of processes, depends on the geometry and the material. If you're running an ice sheet at 1 kilometer or 5 kilometers or 10 kilometers, there's no way you're capturing the details of form drag. So these models that really rely more on the geometry of the bed, like the Weertman tombstone model, they're probably not too unrealistic when you compare them to some of the experimentally derived basal sliding laws, which are really focused on the details of skin drag and assume we know the topography well. You can also start to use these radar data sets to interrogate other processes that are important, like glacial erosion and deposition, to investigate our models of those processes. One thing that's really nice about having these data when you compare it to work that's done on post-glacial landscapes is it's in situ. We know what the glacier configuration is. We know what the stress configuration at the base of the ice sheet is. One thing that's really interesting about the work that we did at Thwaites is that many models of glacial erosion assume that the ice and the water flow in the same direction. because water tends to flow down the hydropotential gradient, and typically ice flows from thick to thin down a similar gradient. But at Thwaites, there are lots of places where longitudinal stresses are really governing ice flow, where actually the surface gradient, these black contours here are surface elevation. In this case, Thwaites is flowing from right to left, but it's flowing uphill, up a surface gradient. And so here's a situation where the water and the ice are flowing in different directions. So now we get to start to test our models of how do landscapes in the subsurface form. I think I'm just going to skip past that for a moment. You saw this slide earlier today. This is a result of Atsu Muto, who collected seismic data over this high-resolution topography that we have at Thwaites Glacier. Seismic data is really useful because it is sensitive to the elastic properties of the substrate instead of the electromagnetic properties. And it turns out that the common substrate materials are easier to discriminate by their elastic properties than by their electrical ones. And so when we go and collect active source seismic data, we can start to tell the difference between bedrock, unconsolidated till, water. Atsu found a couple of interesting things. One, in this upstream area where we have these elongate bed forms in the morphology, we have this kind of uniformly weaker looking material, unconsolidated till. And he can determine that by inverting for a quantity called the acoustic impedance, something that's related to the elastic strength of the material. We also see that on the upstream sides of topographic features that are apparent in the radar data and apparent in the seismic data, we seem to have these really strong beds. We seem to have exposed bedrock. And so now, using this local comparison between seismic data and the kind of qualitative morphology of the subsurface, we can see that the material properties are expressing themselves in the morphology of the bed. And so it might be the case that we don't have to collect seismic data everywhere, which is between 5 and 10 times less logistically efficient to collect. We could maybe use some of this morphological information to infer something about differences in material, differences in strength, prescribe a heterogeneous basal sliding law. We've taken this swath radar, so we took it to Thwaites. We've also taken it to this location called Hercules Dome in central West Antarctica. And one thing that became clear is that when we were looking at the morphology of the swath radar data from Hercules Dome and comparing it to the swath radar data from Thwaites, is that we saw some of these same qualitative differences. These are two-dimensional spectrograms. This that you see here, this kind of bright band, indicates that the roughness in the bed is really anisotropic, that it's essentially smooth along flow and rough across flow. That matters because that seemed to be related to the subglacial properties. So this multi-element array processing allows us to measure bed topography at high resolution. That high resolution can potentially give us qualitative information about bed properties, which it turns out are essential to our modeling of the marine ice sheet instability. Ultimately, we can also use these data to improve our other understanding of solid earth processes. I'm trying to make up time, so I'm going to run through this fairly quickly. But the other technology that we're really trying to implement here is something called multipass processing or radar interferometry. The real benefit of radar interferometry is it allows us to extend these beautiful surface observations we have to really the governing processes. So from Landsat 8 and Sentinel and from the future launch of NISAR, we will have these incredible maps of ice flow speed. But ice flow speed is really the integrated end product of shearing and basal sliding, the two processes that we want to be able to disentangle in the subsurface. And so radar might give us a tool to separate the contributions of sliding and shear to say something more about what's actually happening at the contact between ice and rock. So the way that we do this is built on the principle that horizontal speeds are related to vertical velocities by the continuity of ice. So when ice stretches, it has to thin because you can't change its density. So if we imagine we have this ice column here, here's the base, here's the surface, it's built of all these blocks of ice, and we have side A and side B that are both sliding, but they're sliding at different speeds. Side A is moving slower, side B is moving faster. That ice column strains and it thins. And what we see is this surface moves down by a lot, this moves down by a little, this moves down by less. And if we could measure the displacement of the top of each of these boxes, we would see this profile, where the top boxes move down a lot, This bottom layer hasn't moved down at all because it's in contact with the rock underneath. If the ice flows by shear instead of by sliding, we have a different horizontal speed profile in the ice column, and thereby a different profile of strain in the ice column. And so if we can measure the vertical strain as a function of depth, we can start to deconstruct how much of the ice flow speed is arising from sliding and how much is arising from shear. To do that would allow us to test all kinds of questions about things like subtemperate sliding, where sliding is initiated, how heterogeneity in bed properties manifests across the ice sheet. This measurement, it turns out, is a really complicated measurement to make. And I think I'm running out of time, so I'll spare you some radar theory for a moment and just say that we've made it using stationary radar systems. You've all probably heard of AP-RES, autonomous phase-sensitive radio echo sounders. These benefit from the fact that they're not moving. And so we know that all of the signal is coming from deformation and motion in the subsurface. And what we've done, so Johnny Kingslake in Ross Island and data we have collected at Hercules Dome has allowed us to disentangle areas where flow is dominated by shear and area where flow is dominated by sliding. So you can see this kind of characteristic shear profile, this characteristic sliding profile, characteristic shear, characteristic sliding. So this allows us to extend surface observations into the subsurface to address questions of glacier sliding using radar data. So the technology of doing this from a profiling radar is more complicated because we don't have the benefit of a stationary instrument. We acquire it from a plane one day, we come back a month or a year later, and our precision of the location of that plane is limited. And so we introduce a new component to our radar signal that isn't deformation in the subsurface, it's error in the positioning of our platform. To correct for error in the positioning of our platform, we need to know a lot about the details of the geometry of our target. And it turns out that the same technology that allows us to map the subglacial environment in multiple dimensions, that swath radar technology, also allows us to determine the geometry of the end glacial environment, to correct for errors in the position of the plane, and make this same measurement, this phase discriminating measurement, using a profiling instrument. And so now, instead of from point measurements collected at a single location measuring the end glacial velocity profile, we can do it in a distributed sense across the Antarctic and Greenland continents. And so we've started to test this using repeat measurements that were collected as part of NASA's Operation Icebridge in Greenland. Unfortunately, we don't have a lot of multi-pass Icebridge data co-located with AP-RES measurements, which we're treating as our ground truth, a more proven technology. In the places where we do, we see pretty good agreement of our vertical velocities. But in 2022 and 2023, we collected over 70 of these, I should say Elizabeth Case and some folks at Columbia collected over 70 measurements of baseline measurements for vertical velocity along the central trunk of Thwaites Glacier. This year, I'm going back in 2023, whatever year it is, with a profiling radar to try and collect these same profiling multipass measurements that can be compared against the individual AP-RES measurements to prove the method so that we can start to extend these measurements of end glacial vertical velocity to broader areas in Antarctica. So by measuring subsurface strain, radar can extend surface velocities to end glacial and basal velocities. This is only possible because of the other technological developments that came from radar engineering and signal processing that I mentioned before. And we're really trying to prove this concept in the upcoming field season. So to kind of summarize, I tried to sell the point that the nature of unstable grounding line retreat depends on these poorly constrained properties, the geometry and material character of the substrate. And maybe there's no hope for measuring the bed at the resolution required to get all of the details of the physics right. Radar can be used to identify qualitative differences in material properties, extend some of our wonderful spatially comprehensive measurements from the surface to the subsurface, and ideally improve our treatment of heterogeneous sliding in ice sheet models. So with that, I say thank you, and I'll take any questions.
Thank you, Nicholas. We have maybe time for 2 questions.
Thanks very much, Nick. Hey, can you give me an estimate of what percentage of acquired swath data has been processed?
No.
Ballpark it.
So John Payton, who is the one who first kind of pioneered that technology, and myself and Knut Christensen have a proposal to go and reprocess as much of the Operation Icebridge archive as we can. It turns out, for anyone who's worked with Operation Icebridge data, knows that they're amazing, and also it's research quality data most of the time. It's not a production instrument. It's constantly changing. And so it turns out every additional survey that's collected, there's always a slight stressor associated with processing the data and then digitizing the bed. I would say we have got, well, Operation Icebridge data, which are the ones that I focus on, were mostly collected in Greenland. There's limited coverage in Antarctica. But your interest in CAM, it turns out I've reprocessed some of the data from Willans and CAM. Willans is interesting because the surface seems to be really specular. So what's required to do swath processing is you have to get scattering from off nadir, because you have to get energy from the right, you have to get energy from the left. At Willans, the bed looks like a mirror, which is kind of incredible. It's interesting in and of itself, but it's not great for getting the topography. But we should talk about CAM at some point. Maybe I'll prioritize the data sets that you're interested in because you asked me the question.
Thanks a lot, Nick. Really, really nice to see this compilation. Again, swath, because we discussed it on Sunday and also a bit on Monday in the rings workshop. And the question was, if we do rings, should we focus on actually also collecting swath data because of the obvious advantages you presented? So what would be your take on that, given the experiences you have, not only what the data looks like with weights, but also the implications for the whole dynamic behavior?
That's a great question. So swath, the widest swath that I've seen generated is about 3 kilometers wide, which means that if you wanted to create a seamless topography, you still need incredibly dense line spacing around Antarctica and Greenland. And so you run into many of the similar issues associated with data gaps, even with swath topography, if you're sampling at 5 kilometer line spacing. That doesn't mean that there isn't a lot of very useful and interesting information in swath data that you collect that isn't seamless, where you have overlapping swaths so you can constrain uncertainties at wide angle. And so I think the more data you collect with this, the better sense you get for details in multiple orientations. I still think that there are challenges. Like, this is not a panacea to the problem of mapping all of Antarctica and Greenland at high resolution because the swath width is just too limited. You know, if the plane were flying at 10 kilometers and you had a high enough power that you could see off to wide angle and you could discriminate all of your targets, maybe you could do something that's seamless. But I'd say the benefits for a single profile around the ring of Antarctica are more marginal than when you can do these denser surveys. I still advocate for it. I mean, I think you can do incredible things with these data. And one thing that stands out to me is looking at anisotropy and the roughness of the bed. It's clear that that matters for sliding. When the bed is smooth in the along track direction, it basically doesn't matter how rough it is in the across track direction for basal friction. And so that's important. You know, in the rings mindset, there's the primary and interior and exterior rings. For your interior ring, I think that's really quite powerful, a useful thing to do. For the exterior ring, it's also probably useful if you wanted to eventually try and do interferometry to look at melt in ice shelves, because you need the additional multi-element data. But I would say from a bed topography mapping, if your core goal is just calculate a flux gate, I don't know that it helps you. It's not a step change in the quality of the data that you get.
Thank you again, Nicholas. Next up, we will have Robert Law on complex motion and